Hello, nice to see you again in the new year. Today we will go into I would say, almost the final uh, chapters on the control, right? So today's topics would be on the design using the root locus technique. Remember last week, last week we did learn about root locus technique. Okay, we mentioned. So today's our goal of the day would be to design the compensators for a control system. As you can see from the diagram shown, okay, I have tried this in Scilab X course. Okay, so you can always try this on your own as well, right? Where you can obtain the time response of your system by controlling the K, the gain itself. Remember last in your root locus technique previously, uh, you are able to select a proper gain value, the K value itself. Okay, so you can always assign it in your X course. Okay, by typing in the set context, you just type K equals to define your variables. Okay, or if you don't like this method, you just type directly 23.72 as usual, right? So you can see that the performance of this system itself, right, when given a gain of 23.72, but you realize that this system may not be optimal as you want, right? You can see that there is a big error gap in between the input as well as your output and so on. Okay, so to a bigger pictures, what you have learned throughout these few weeks or maybe 2 months, right, is that you can now able to at least read a block diagram. Okay, so this is a block diagram obtained from a menu itself, okay, by Mitsubishi Electronics. Okay, so this block diagram actually is related to a PLC control of a PID. Alright, so this is what they call PID control, where in a industry itself you would want to control your process, okay, particularly, or maybe a system itself where you want to control maybe the flow rate, velocity, maybe temperature and other things, okay, mixing ratios and other things. So this is where the control come into a picture, right? So as we can see as well, in this picture itself, this is where the control, which may be a bit of electronic, right? So you can see this is a PLC panels where they may connect to the PLC controller, right? Where this PLC controller maybe is in terms of a temperature control, right? So this is where you can see it's a very simple temperature control, but then internally it is a programmable, where you can see the specifications of this temperature control unit. You can see the terms programmable on off, P, PI, PD, PID. Alright, so now comes into your mind, or bigger pictures, that these theoretical ideas have been actually implemented. Okay, and this is how they can actually control the operations or the process itself, right? So you can always control the P, the PI, or PD, and so on. So what are all these things? These are a controller, or we would say a compensator, as we started with our cost outcome earlier, right? So it's a compensator to compensate our system such that it behave as what we would want it to be, right? So a brief review of the root locus. As we have seen previously, the root locus itself, you able to design for a closed loop system by using an open loop pools, right? So you remember in the root locus techniques, you are using open loop pools, okay, and you draw the root locus of it, and from there you would able to select a proper point, okay, where the gain itself would display or exhibit the kind of performance that you would like to have, right? So that would be related to the transient response. Okay, so from that S plane also, you would also able to know when the stable and the unstable states of the system will occurs, right? That would be a quick review of what you have learned previously, right? But then in our previous systems, during the design stage, okay, you are only allowed to choose a proper loop gain. Remember, you are selecting the point where the gain is actually located at the root locus itself, right? So that would be the limitations of the previous design. Okay, so now today's we would quickly go into a bigger picture, okay, or overall pictures of it, okay. So remember, you have selected in the root locus itself the k value. The k value is actually referring to the proportional control, okay. So proportional control is controlling the k value where you multiply by these factors, okay, proportionally. So we call that as a proportional control, and these proportional controls actually would able to decrease the steady state error, okay, when we increase the uh, gain or the k value, right? So when we controlling the k, we are actually using a proportional control, right? But then the limitation is that using this proportional control, we can only reduce the steady state error, but the steady state error may still exist. It's still not zero, okay, it's only being reduced, okay. And that particular systems, if we are not uh, particular on the maybe a tracking system, we say no tracking requirement, like you don't need to actually detect the exact locations, for example your printer cartridge movement, okay. If you do not care about the exact positions, as long as it moves to that particular point, okay, near to it is okay, then you don't need to have additional things, okay. That steady state error is not zero, no problem, right? Like temperature, it, if you set the target is 37 degrees Celsius, but if you get 36.8, is still okay, then fine, right? But then in certain requirement or applications, you may need to have a steady state error equals to zero or zero steady state error. Then this proportional controller may not be able to actually solve your problem, right? So today's objective would be to design by selecting a proper compensator in order to improve the desired, maybe the transient response or maybe the steady state error, okay. So here we say the steady state performance is referring to the steady state error, right? So this is the whole pictures or the final piece of the puzzles that we have gone throughout the course, okay. Earlier that we start to learn from the transfer functions, block diagram, S-plane, then we know about the transient response on a second order system, the steady state error, right? Then slowly we move into the root locus, okay. From the root locus, we are looking for the range of k that are stable, and also we could able to select the proper k value, right? Now today's would be on the last part where we, after we select, okay, we would also want to compensate or to obtain what we actually require, okay, based on our target, right? A quick briefing on what you are going to do today is that let's say you want to improve this transient response, the idea behind it, what is it all about, right? So let's say you have a desired transient response, okay, from your original root locus technique, okay, that you have, okay, I guess this one is the same problem that you have gone through previously in our previous lecture. You have seen that this is the performance that we get previously, right? This is the performance that we get previously, okay? But then if we think that, you can see that the peak time is about 6 seconds. If we say, and the settling time is about 10 seconds, if we would want to make this faster, our goal is to speed up this response, okay? Then therefore we would want to have the so-called solutions or the root locus actually shift to point B. Alright, if you don't want to affect the percent overshoot, we still select a root locus lying along the radial line. Okay, but then if we select the point B itself, we will notice that this point B actually doesn't somehow located in our root locus, but point B itself would be able to make our response faster. You can see that the red line represent the point B, okay, which remain 20% overshoot, okay, but then the settling time would be about 4 seconds, right? So you have improved the settling time by 2.5 times, right? Therefore, in order to shift from point A to point B, we cannot solve it through selecting a gain value, the K value itself, okay? Therefore, we need another tools, okay, or methods to actually solve this problem, okay? You can see that point B is no longer exists on the previous root locus, okay? Therefore, we have to use a new method to actually shift the root locus, okay, such that the point B actually pass through this root locus, okay? What we can do is either we change the parameter of the original system, okay, means you add a system or you change the systems, okay? That would be a difficult and expensive. The second methods would be, the easier part would be to add a compensator, right? So this controller or compensator itself have two main purpose, right? Depending on your design requirement, okay? The first one, as we have gone through, okay, is either you want to improve the transient response, make it faster, or make it fall into a certain range of settling time or peak time. Okay, that can be obtained by using a differential based controller. The second one would be to improve the steady state performance. Remember our previous problem is we say for a system or applications that require tracking, we cannot tolerate like a non-zero steady state error, right? So we would want to improve this kind of steady state performance, okay? And this can be obtained by using a so-called integrator based controller. So this differential and integrator terms actually comes like, remember you have a Laplace transform differentiations and integrations, right? If you are doing an integrations using a Laplace, you have a 1 over s, okay, whereas if you're doing a differentiations, okay, using a Laplace transform, you will multiply by an s, right? So that would be the idea to modify the system or the transfer functions of your system itself, okay? There are two types of placement where you want to locate your compensator, either cascade or in the feedback. Alright, so you either you put it at the cascade, okay, along your open loop directions, or at the feedback directions, okay. But in our discussions today or in this course, okay, we would only focus on the cascade, alright, whereas the feedback compensator, we would not go into it, okay, because it may be require more times, and our main purpose of this course may only to expose you with different type of technique in the control only, right? So once you have this basic knowledge, I believe you can easily go through the feedback compensator later on your own. Okay, if you are required to do so in your future um, applications. Okay, this is how you can see we could able to improve the steady state performance by without affecting the transient response by adding an integral. So this is the integral in the Laplace transform form 1 over s, right? Okay, and by adding this, actually we are changing the type of the system. Remember, if we increase the order or the type of the system, the steady state error will actually reduce or become zero, okay, depending on the type of input. Okay, if the input type is at the higher order, instead of step it may be RAM or others, then we have to further increase our type of system. Okay, this is how we can actually improve the steady state performance of our particular system. Okay, we add an integrator or as our compensator or into our controller. So now we come into the the ideas of, you heard me talking about integrator, differentiator, okay, as well as the first one, the proportional, right, the gain itself. Okay, so basically it makes up of three terms: P, I, and D, right? And this is what the previous pictures, remember the bigger pictures, okay, where you have a temperature control unit that allows you to program the P or PI or PD and so on, right? So this is where it comes into the picture, where you have the P, okay, to control the feed of the scale of the error itself. When you feed it back, okay, you are trying to magnify or reduce the signal of the error itself, okay, the P itself. Or in the integrator, which is used to improve the steady state error, and the D to actually control the transient response of the system, okay, to make it faster, okay, usually, right? So this is the picture, and when we combine it with the P itself, okay, when we combine it with the P, then we will have a PD, PI, or when we combine three of them, then we have the PID, right? So this is where the naming of the compensator or the controller comes. Alright, so the P, the I, and the D. First, we would look into the improving. Remember two functions, okay? We look into the first part, okay, improving the steady state error, meaning to say we reduce the steady state error, maybe making it to zero, okay, zero steady state error. We would want to use the integrator as our compensator. Okay, so when we add a integrator as our compensator, we would able to eliminate the steady state error, since it increased the system type. However, what would occur is that the desirable open loop, you can see this, you have 3 points which located here, but then when we add this particular integrator, then we will add an additional pools to our existing root locus, and that would shift or change our root locus, right? And because of that change, this point A will no longer exist on this particular point itself, even though previously we have selected this point. When we say this point can satisfy our conditions, but when we add this integrator itself, then therefore it doesn't able to fit into our new, right? So you can see when we we add this additional pools itself, the root locus actually change, right? And this point A is no longer lying on the root locus of the new system, right? So the load locus is lying on this green line, and this, okay, no longer on the previous one. Okay, therefore, even though we are able to so-called improve the steady state error by reducing the steady state error, okay, to a zero, okay, but then point A is still here, right? It doesn't lies into our root locus. That is the main problem, okay. Therefore, what we should do is we add a gain, okay, or by reselecting the gain itself, okay, such that it lies on our particular system. Therefore, when we come or when we use the integrator itself, we usually pair it with a proportional, okay, the p itself, because we want to reselect the gain, okay, such that that gain give us a solution that lies in the root locus on our new root locus, okay. Therefore, we always use a pi instead of an I compensator, right? So this is the reason why we always use pi, and you can see that the k is here, and this is the integrator itself, right? So the integrator itself. So the integrator itself, you can see you may want to use this transfer functions of this pi controller into your transfer functions, okay, in order to manipulate or to increase the system type of your system, okay. This is what we call as an ideal integrator, all right, where you actually add a pool to the origin, okay. You are adding an additional pool to the origin itself, okay. We call that as an approach number one, okay. But then we have another approach, we call it as a non-ideal integrator, okay, where instead of putting a pool into on the origin itself, okay, but in this non-ideal integrator we put a pool close to the origin, okay. And if you would want to use this non-ideal integrator, we call this compensator as lagging compensator, okay, lag compensator, which have this transfer functions. Again, you have the gain, okay, and this lag compensator comes together, okay, just like this p and the I part, okay, that's come together, right? So you have two approach that allows you to actually improve or reduce the steady state error, right? But why there are two approach, okay? The first approach can give us the exact so-called zero steady state error, but then it actually requires an additional active element which you need to power it up, okay, additional maybe devices, okay, and because of that it may be more expensive, okay, by adding additional devices, okay. But then if we would want to make it cheaper, okay, but still obtain our purpose, therefore we can use this non-ideal integrator, okay, which only require a passive element, maybe few electronic components, okay, and tweaking into the programmable part, right, and that would solve our problem, right? So you have two approach, okay, that we will go through later on. Both approach have the same purpose, okay, by adding a zeros, okay, as to the pool, right? Both approach have added a zero in additional to the pools, okay. You have a zeros, okay, as well as a pools, all right. So you can see that in beside when we use this integrator itself, okay, remember integrator is only 1 over s, okay, but when we come into the real implementations, we still add a so-called zero to our system, okay. This is to actually I would say reduce the so-called additional pulse effect on our system, right? So you will see that comes into play later on. So how this PI compensator can be selected or works? Okay, first we would include a pull at the origin. All right, remember we have the equations like this, okay, for our compensator. But what is the value of K and what is the value of A that we need to select, right? That is the value that we need to select, okay, in order to design for this compensator, for this PI compensator. Therefore, first thing first, we add a pole at the origin, okay, which corresponding to this S at the bottom, okay. Then we include a 0, okay, and this 0 represent this S plus A, okay, on this, and this 0 must be on the negative real axis, okay. This 0 lies on the negative real axis, okay, but if possible close to the pole, okay, so that we are just like mathematics, okay, we add 1 to one side, we minus 1 at the other side, right? We try to minimize this so-called effect of adding a new terms or parameters into our system, right? But then if we put we don't want to put this 0 at the origin, okay, we just put it close to the integrator poles, okay. So this is our ideas, right? So you can see that the poles at the origin, and this A value is your task to figure out what is the best value of this A, okay. You can always try it on your own, okay, any values that you prefer. All right, so in this case we just play around with a value, okay, just put minus 0.1, okay, assuming it's close enough to the 0, right? If later on you found out this 0 doesn't perform as you want, then you can further make it smaller, okay, minus 0.05 and so on, so that it perform as what you intend to, okay. But for our purposes, illustration purposes, okay, we just assume the 0 as minus 0.1 first, okay. Therefore our A value would be 0.1. Once we put A value equals to 0.1, then our compensator, our PI compensator, will have this parameter K multiplied by S plus A 0.1 divided by S, okay. The K value, which represent the proportional part, we still put it as K first, okay, such that after later on we would able to reselect this value of K, right? Okay, so by doing so, you can see that this point okay, that particular point will actually improve later on, right? In order to implement this PI or these functions, okay, into our system itself, you can actually break them into two: the P and the I, right? Where this P would be a K value, K1 value, and I would be the K2 value, okay. These are the mathematical manipulations of it later that you can play around later on, right? So as you can see, we have these transfer functions initially, right? When this K value exists there, we can actually break them into K1, okay, bracket S plus K2 over K1, okay, and this represent our A value, right? You have S plus A, remember? So this would be your A value or the 0 value, and this K1 would be your K value, the gain value, okay, that you can play around later on, right? By selecting this, after you get your whole system, then you will check what is the K1 and K2, and you can put it in or program it into your controller. right? So this is the idea it is. Okay, so once we have select it properly, therefore later on you will see that originally is the black line which have the steady state error of 0.108, but then if we add an integrator, then it would be in the green line. Okay, this green line, right? So and this steady state error will equals to 0. Okay, but you can see that from this diagram itself you still see a gap, right? It's not 0. This is because 10 seconds is not long enough. If you plot it maybe 20-30 seconds, this would eventually comes to 0, right? But what happened is that this integrator actually slowly compensate the 0, okay, and it being lag behind. Okay, you can see this red line, this green line actually slightly lagging behind the the black line. Okay, so we can say that when we add or we put this integrator itself, the effect would be slightly lagging. Okay, that's why this lag compensators idea actually comes into play, right? This is where you can also improve the steady state error by using a common functions that behave similar to an integrator, right? But then this integrator itself will have a 0 and a pool. Okay, the ZZ, the compensator 0, and the PC, the compensator pools, right? That you would want to put instead of a pure S there, right? How to select these two? We will start with the PC first. Okay, again, this selections is up to you as a designer. You may want to use minus PC, okay, because we want it to be a negative value, right, lying on the rail axis. Okay, but as close as possible to the 0. Okay, as close as possible to the 0. So the pools is not origin but close to the origin. Okay, this is our selections guideline for your PC. Okay, then after we have selected the PC, then we would want to select the 0, and again this 0 should close to your PC, right? Close to your PC, but then make sure it is on the left hand of your PC, meaning to say in your S plane lying to the left of one point, meaning to say the value is more negative, right? So you have to select a 0 value that are more negative than your pools, okay, your PC value, right? So for that purposes, okay, again you can always select any value that you would want to do so, right? But when we come to applications, you may want to design with a certain target, right? So let's take these applications, okay, as our examples. Okay, so our applications would want to improve the existing steady state error by 10 times, okay, by a factor of 10, okay, with a damping ratio of 0.174. Okay, so if we would want to improve the steady state error by 10 times, okay, why this would comes into this so-called lag compensator? Remember, in the PI compensator, if we use the ideal one, the steady state error will become 0. Okay, but if we are using this so-called non-ideal compensator, which is this lag compensator, problem is that it will not go to 0, but then you can tremendously reduce it to a rate that you want. Okay, for this case we would want to reduce it by 10 times. Okay, so if we would want to know how much is 10 times, then first thing first, you have to figure out what is the existing steady state error. Okay, so you can check what is the compensator before the the steady state value or the constant, okay, before you add this lag compensator, and we compare it with after the compensations. Okay, so you have the kV, remember the kV value, which is corresponding to the steady state constant, right? Okay, so we have kV, and which is kvo, okay, and kv new, right? So if we add a kv new, what we actually add is that we add this z over p, okay, to our kv value, right? Okay, so meaning to say, when we add this to our uh, our solutions, okay, therefore here we would see that it's actually this ratio z over p multiplied by our previous or existing error, right? Existing error. So therefore, by using this concept or this idea or this knowledge, right, therefore we can select the proper ratio of z over p, okay, that meet this requirement of 10 times reductions. Okay, so for this k value, or let's say now this is a positions problem, so we use kpo, which we obtain as 8.23, right? If we would want to reduce it by 10 times, okay, 10 times, so we should get roughly 0.0108. Okay, let's say this is so millimeter, right? So based on this kp, our error would be this, okay, and reduced by 10 times we get this, right? So in order to reduce 10 times this value, we have to change, okay, according to this factor, right? So what we can do is that we know that error is 1 over 1 plus kp new, right? And based on this, you can actually calculate 1 over 1 plus kp new. This is our steady state error, okay? You just solve it, you will get the kp new as 91.59. Okay, meaning to say, if you get 91.59, then we would be able to obtain a 10 times reductions in the steady state error. Okay, so in order to get this 91.59, okay, what you need to do is you get this ratio z over p as your ratio. Okay, so the ratio would be 11.13. Okay, so 91.59 divided by the O value, right? Divide by the O value. Okay, so you get 11.13. Okay, so based on this 11.13, what you need to do now is that you start with your random preferable PC. Okay, so let's say we select 0.01, okay, and then therefore your ZC, okay, based on this ratio, which is 11.13 times of this value, you would get 0.1113, right, as our ZC. Okay, so eventually this is our lag compensator, right? You can see that how we can apply our previous knowledge, okay, into our compensator selections. Okay, you just start with one PC, then you would able to select the next value, right? So once we get that, okay, what actually occurs is that this is our original point, okay, And once we so-called add to our system this particular lag compensator, okay, you can see we actually add this additional pulse and zero at this point, okay, which is very close to origin but not origin, right? And it actually shift from the blue line to another blue line, right? So if you plot it out carefully, you can see actually two road locus over there. One is old and one is new, right? So our new value, if we are using the old value, which is the blue color, the K value should be 164.6, whereas in the new system, okay, which after we add this lag compensator, our new value should be have a gain of 158.1. Okay, so we have reselect our P value or the K, sorry, the K value, okay, which is the gain of our system, okay, and which this is the performance of our system. Right, you can see that this is the performance of our system, okay. And if we look closer, okay, this is how you can see the gap. Right, the problem is if sometimes you will randomly select, you don't want to use or to start with a PC as negative 0.01, okay. If you happen to select like 0.1, what happens is that if it is not close enough to the origin, then you can see that your zero, okay, the 0 point here, okay, is now somewhere in between your other or your system pools, okay. Previously, if we select close enough, your original system, which is 1, 2 and 10 is here, right? Whereas this is the pulls and zeros due to the lag compensator, right? But if you select if your selections of PC is not close to the origin, therefore you can see that the zero is now lies in between these 2 points, okay, in between these 2 points, and that would actually affect your performance of your system later on, right? But nevertheless, is still able to improve, okay. Our final outcome would be to reduce the steady state error, okay, without actually affecting much on the transient response. You can see very close to your previous transient response, okay. So any questions so far? If you have, feel free to put into the chat box, okay. So we will go through it when the times come, right? So we will proceed to the next functions of a compensator, okay. The first one we have deal with is the improving the steady state performance, okay. Now on the second part, improving the transient response, okay. On the transient response, the idea is very similar, but then instead of using the integrator, we are using a differentiator. Sorry, this should be differentiator, PD, right? PD, differentiator, right? So just correct this one, PD, right? So the PD functions will have this K multiplied by S plus ZC, right? So you can see that now in this ideal different derivative or differentiators compensator itself, you don't have this pools anymore. You only need a zero, right? So again, the purposes served by adding a zero, okay, which act as a differentiator, okay. But then if we are using the ideal one, you still have the same problem, okay. You may get a better performance, okay, but then you require maybe expensive or active elements, all right. And at the same time, because of you are adding this particular terms, okay, you may actually amplify the noise if it is if your error is high, okay, means you have a lot of noise, okay. So you may amplify the high, so-called high frequency noise, okay, that it feed back to your system, okay. So that may be the so-called disadvantages of this PD itself, right? If you would want to use a second approach, which is a non-ideal integrator, then therefore it have a reasonable performance, not a, a best performance as we want, okay, but then reasonable performance that meets your criteria. At the same time, you don't need a so-called active elements, and because of that also it is less sensitive to the high frequency noise, okay. This is the approach, okay, that you can use to actually improve the transient response, right? So if you again not take a closer look, okay, of this non-ideal integrator itself, the equation is exactly the same, okay, for this non-ideal integrator, okay, sorry, differentiator, right? So this should be differentiator. So you can see that this differentiator itself is exactly the same with the non-ideal integrator. It only depends on the selections, okay, of this Z and P, okay, that make it become a lag compensator or make it as a lead compensator, right? So that is the only difference on your selections of the value or the ratio itself, okay. But we will go into the details later on, right? So this is the performance of your previous system, right? You have the K value equals to 23.72, right? So if we intend to improve the transient response, okay, therefore we now need to shift this point away, okay. The further away it is, the faster it is, okay. If you want it to be moving faster, okay, you want to shift it further, but then because of it's no longer lies on the root locus, we need this derivative compensator to do the job for us, okay. We add the zero, okay, we add a zero to our system, okay. And when we add the zero to our system, you can see that we actually shift the root locus, okay. Because of this zero, it cancel out the existing zero, the existing pool. So therefore these two pool now act like a second order system, right? So that is the idea behind it, right? So you can see that we have able to shift the point from A to B, okay, with a new gain value, the K value 51.25, right? So as we can compare this compensated pools will have a more negative real and imaginary part, okay. You can see that it's actually shift it, okay, to a more negative real value and more or greater value of imaginary value, right? So this is the idea of splitting up or adding a zeros to our system, okay. From the implementation view of point, okay, you can see that it's very similar again, okay. We have the equation itself, we can break them into a parallel, which is a combination of K2S, okay, and the K1, right? So when you combine them together, this would be our combined transfer functions. And from this again, you can see that the terms itself, this is the K value and this is the zero value, okay, that you would want to tune, okay, later on, okay, based on your calculations, right? So here is the performance of after you shift it, okay. Before you shift, this is the performance, right? and after you shift it to a new point, it actually shift or move faster. Okay, you have eventually speed up the peak time. Okay, you can see that the peak time is around 1.6, 1.7. Okay, it's now reduced to maybe 0.4, right? It's shift, okay, it's speeded up, okay, by adding this PD compensator, right? But then because of this PD, okay, remember, if we increase the gain, the steady state error will reduce, okay, but still not zero. Okay, that's why you can see that the steady state error is still exists, okay, but then the performance have actually improved, right? So how we can do that? Okay, this is an examples of how we can implement it, right? So let's say in our applications you want to reduce the settling time by a factor of 3. Okay, means we want to make it faster, okay, the settling time by 3 times, okay, with an overshoot of 16%, okay, while maintaining the damping ratio. Okay, so let's say the damping ratio is corresponding to this radial line, right? Okay, and it's also related to the overshoot. Okay, so first thing we have to figure out what is the damping ratio that corresponding to this 16% overshoot, right? Since this is a third, yeah, third order system, okay, no, this is a first order system, right? So since first order systems, if we add, then it's second order system, then yeah, maybe we can still play around. Okay, oh sorry, this is a third order system, okay, type 1, okay, type 1 but third order system, okay, which you have the s to the power of 3, okay, third order system, but we would want to assume it as a second order system. Okay, the assumptions or the approximation of second order system, you have gone through it on your previous uh, lecture, right, on the root locus technique. Okay, remember, we have to justify whether the approximations of second order system is valid or not, right? But then never mind. Okay, now we just treat it as a second order system. Okay, why we always treat it as second order system is because we would want the pools, okay, which usually only 2 point, one is on the positive and one is on the negative, which is a conjugate pair of a complex pools itself, okay, close to the origin. Okay, when these 2 points actually close to the origin, we actually call this as a dominant pools or dominant solutions. Okay, and our system actually behave based on this dominant pools. Okay, whereas for the pools which lies very far away from the origins, the effect is very less. Okay, that's why when we try to approximate this so-called second order system itself, we actually look at this particular criteria, okay, whether the pools or the third pools actually lies close to the origin or not, right? Remember that, right? So you can always look at that, but nevertheless we assume that this is a second order system, right? Treat it as a second order system first, okay, during our design. So therefore you can use the second order system equations to identify what is the damping ratio. Okay, just flip back to the previous equations, okay, how to get this damping ratio for a second order system. All right, so you can draw your line, right? So based on that, you will see that the dominance second order pools would be this point and the conjugate, right, which is very close to the origin. So this would be our dominant pools. Okay, the third pools, which is the point C itself, okay, which is we can say so-called negligibles. Okay, so this is our approximation that you may need to do later on, right? So we will start with this first. Okay, based on this dominant second order pulse, we can estimate the settling time. Okay, 3.32 second, right? So if we want to reduce it by 3 times, meaning to say we divide by 3, then our settling time, our desired settling time would be 1.1 second, right? So in order to get 1.1 second, using our second order systems equations, we can actually predict it by controlling the real axis value and the imaginary axis value, right? So it is related to the settling time and the damping ratio, right? So this is how we can do it, right? So this is damping ratio, which is which is estimated as 4 over PS, our settling time, which is 1.1. You just substitute in, then you get this 3.61, right? So you just refer back these equations in your chapter 3, right? Then once you get this one, you can get the imaginary value as the real axis. Okay, this sigma, okay, multiply by tangent your angle, right? So you would get your particular values of imaginary, okay, which is 6.193. Okay, so this 120 is your values that you get, right, previously, remember, related to this damping ratio, right? Damping ratio line. Okay, 120.26. Okay, so this is the one. Okay, so if you realize in this diagram that I have obtained from Scilab, right? Just come into mind is that in computer they can plot without so-called yeah, they can plot according to values, right? Okay, but then if we print it out and we try to measure this angle is not 120, okay, because of this gap of x-axis and the y-axis is different, right? You can see that they are different. Therefore, this angle, if you measure it on paper, is not correct, right? So if you want, you just make sure that the length of this x and y axis is exactly the same, right? But then we just use this as our examples. Okay, computer plot it correctly. This is 120.26 in the computer sense, right? And you can see that this is being reflected by this unit. Okay, this is actually 1 unit, okay, radius, which is, you can see, is not a perfect circle but it's an eclipse. Okay, means the real axis actually have a longer than the imaginary axis, right? So from this equations, okay, that allows us to obtain a threefold reductions in settling time. We have to shift this point, blue point, okay, or pulse, to this new point, right? This new point, okay, which is obtained theoretically, all right, by these two equations. Okay, so how we can actually shift it to that particular point is that we would use that particular new point as our design point. Okay, this would be our new design point. Okay, and in order to get this real design point, okay, we would want to know what is the zero. All right, remember, we in the PD compensator we will add a 0, right, to our system. Okay, but the angle we may not know, right? So what we can do is that we take this new point, okay, then we start to calculate, or if you want, print it on scale, you measure it. Okay, otherwise you can always calculate based on the trigonometric relations. Remember, this is just a Cartesian's graph, right? So you can always get the angle by tangent, okay, opposite and the adjacent length, right, or adjacent side, okay, to obtain this degree, okay, or the angle itself, okay. So you can always backward calculate of all these three, right. So this is the value that you may get, right. So what you can do is that you sum all these angles, okay, of all your poles and zero. If you have, since we only have 1, 2 and 3 poles, okay, we don't have zero, then we don't have to add them up together. So you just have to use all the angles to the new point, right. Calculate all these angle, total them up together, which happens to be 275.6, okay, 275.6, okay. Why negative? Okay, ignore the negative there, right. 275.8, okay, that would be our so-called result of summations, okay. Then what we can do next is, in order to get this angle refer to the difference between this result with the 180 degree, okay. Why 180 degree is that? Remember, in our root locus technique, in order for a pulse to lie on the root locus, it must satisfy the summations of odd multiple of 180 degree. Okay, so this is the idea. Okay, odd multiple of 180 degree. Okay, so therefore, because of this, okay, we would want to see what is the difference, okay, needed to adjust, okay, and we obtain 95.6, okay. So therefore this angle should be 95.6, okay, for us to put in the so-called zero, right. So from this figure, using a trigonometric relations, okay, we have these points as 6.193 divided by the difference between the 0 to the real axis, okay. So you can use 3.613 minus, let's say, it lies over here, right. So this minus this, alright, so you get the difference, okay, equals to the angle itself, right. So you will get the new value of this equals to 3.006. okay. This is how you can get it, alright. Why we use 180 minus 95? Because this is 95, right. We are calculating this angle using the trigonometric relations, okay. So this one, how to use it, you just draw your trigonometric relations, okay, so that you can visualize where is the locations of the zero, okay, whether you should use 95.6 or 180 minus 95.6. okay. So now, after we add that particular, or after we have selected that particular zeros, okay, therefore now you can see that I replot it using the new selected value, okay, which is 3.006, okay, 3.006. Therefore you can see that now our design point is actually passing through the root locus, okay, just like magic, right. So you can see that now it have shifted from point previously somewhere here, okay, shift it to this point, but still lying along our new root locus, right. So this is what we want to do, okay. After we obtain this root locus, how we can get this k value, you can always refer back to the chapter 6, okay. Either you use computer, remember, by plotting it, then you just click it, right, using a data tip, or you can use, remember, the product of length of poles, okay, divided by of lengths of zeros, okay, to get the k value, right. So That is the idea of how you can get the k value after that. Okay, so once we get that particular performance, you have to justify whether the second order approximation is good enough or not. Alright, so what we can do is either you check it properly, okay, check it properly, or you do the simulations. Okay, so you may want to do the simulations. Okay, so this is a simulated in the x course, right? And you can see that uncompensated, the black line itself, which is the settling time is about 3 seconds. Yeah, settling time is about 3 seconds to the okay, somewhere here 3.3. okay, somewhere here. Okay, it's come to the 2% plus minus, right? Whereas on the compensated part, okay, the blue line itself is actually settles around here, 1 second plus. Yeah, 1 second plus. Okay, so you can see that now it meets our criteria, right? So obviously this is theoretical calculated. Okay, when you simulate it, it may be slightly different. That's why you can see that simulated value is 1.2 roughly. Yeah, roughly 1.2. Okay, so this is how you can justify whether the system is actually designed according to your performance or not. Okay, after you do it, either you do your justifications of second order, or you can simulate it, alright, to check whether the graph that you obtain is good enough or not. Okay, if not good enough, then redesign or reselect the values. Okay, then another methods would be the non-ideal concept. Okay, in this concept we would use the lead compensator to improve our transient response. Okay, here the advantages, as we have mentioned previously, is cheaper, is less noise amplifications, but the disadvantages would be it doesn't reduce the number of branch. The problem is you have a zero as well as a poles there, right? So you will have this ratio of z over p, okay, still exists on our system, but the way of our selections now is to make our selections to influence the system or to compensate the system such that it's improve the system. Now remember, recall back, okay, by putting this compensator, you have shifted the line forward, okay, nearer to the earlier part, meaning to say you would want to have a leading type of response. Okay, you lead it before your previous one. Okay, so we call it as a lead compensator, whereas on the previous concept we want a lag compensator, right? Equations remain the same, only the selections of values is slightly different, right? So how to select this value of ZC and PC? First, we would want the PC value more negative than the Z value, okay, the zero value. Is it something different, right? So you can see that the shifting of the zero and the pulse positions, whether it's left or right, will affect whether it's become a lead compensator or a lag compensator, right? Just take a quick applications or examples. Okay, using the same problem. Okay, we want to a threefold reductions in settling time, which is 1.1 second, and we would get the desirable design point would be minus 3.6 plus minus j 6.2. Okay, how we would want to select is that we would start with any value of 0, ZC. Okay, you just choose any value of 0. Okay, now 0 is a free point that you would want to choose. Okay, and this 0 will actually varies your selections or the choice. Okay, so you can see that the choice of your ratio will actually affect the static error constant, and also the gain value. Okay, because of the change in the ZC and PC, therefore the gain value is also different. Okay, then also because of that, the justifications of second order assumptions also are also different. Okay, so first thing first, select any values of 0 that you think is good enough. Alright, so just a hint of where you should select is that, if possible, I would select a 0 that cancel out a pole. Okay, that would be the best. Right, so you can take another s plus 4 or maybe s plus 6, okay, as you want. Okay, but the choice is yours. You can also take ZC equals to 1, minus 1, and so on. Right, so it's up to you. Once you have this 0 itself, now you would want to check what is the PC required to meet this so-called criteria. Right, so in order to get this PC values, idea is still similar. You still need to deal with the angles. Okay, remember the odd multiple of 180 degree. First thing, first you need to do the summations of angle of both the 0 and the poles, okay, to your design point. Okay, to your design point. Okay, then again you check the difference between them with 180 degree and find the locations of the compensator pools. Okay, because you already add this 0 here. Right, previous method exactly the same. Right, only difference is that now, because we have selected a random 0, okay, you have to add this random 0 into your equations as well. Okay, the same methods. Right, so now just take ZC equals to minus 1 randomly. Right, from that, because of the calculations, remember previously we said 0 minus pool, or maybe pool minus 0. Okay, therefore you would use the theta c equals to theta 0 minus pool. Okay, let's say theta 0, which we get once we select ZC equals to minus 1. Okay, you can calculate this angle. Right, minus the summations of all these three. Okay, so all these three previously we get 275.6, so the difference would be 162. Okay, so the minus, positive, negative, it doesn't matter actually. Okay, as long as, sorry, I think I missed the negative. Okay, but then positive, negative is, doesn't matter, as long as you can find out what is the difference or the angle, okay, that contribute to the selections of your pool. All right, so once you get that, again minus with 180 degree. Okay, so you get the difference would be 17. Okay, meaning to say you have to add an additional pool, okay, which is 17.28, the angle. Right, so this angle should be 17.28. Okay, therefore, by again using the trigonometric relations, now you don't need the 180 degree minus 17, right, because this is your exact angle. So you just use this ratio, 6.193 divided by the distance between this particular point, which is 3.613, and this PC point. Right, so PC minus the 3.613. Right, so you should get the PC value. Okay, solve it numerically, you should get your PC value as 23.52. Okay, which is very far away, but then for illustrations I just put it here. Okay, for sure this is 23 somewhere here. Right, so the sign of this PC is negative. Okay, remember you are on the negative, yeah, the negative side of the real axis of the or the S plane, right? In order to get the K value, just again refer back to the methods that you have learned previously. You can use this. Okay, the K value is uh, the ratio between the product of finite pulse length, okay, divided by the product of the finite zero length. Finite zero is the blue line, okay, this line, okay, the rest is the pull length, right? So you should get 915, okay, you should get 915, meaning to say in order to get this point you should add these two particular pools and zeros and with a gain of K915, okay, into your equations. Okay, so this would be your compensator equations, okay, which is your lead compensator equations, right? 1 and 23.52, right? So what we get later on is this is the performance, right? You just simulate it, right? Plot it out the root locus, okay? You can see that it's actually passed through as the design point, okay? And I use the data tip, okay? I also get 915.5 roughly there, okay? So meaning to say our previous calculation is correct, right? But then the question is whether this second order approximations is valid or not. That is the questions, whether it's solve our problem or not. All right, so remember in the design it's always an iterations. You should try a value, calculate and check, okay? If it doesn't meet, then you further improve with different value again. This is the purpose. That's why at the end I still ask this question again, whether it meets or not. I always check. All right, so when you check it with the performance, you can see that yes, it has reduced or changed the so-called positions, right, of the peak time and settling time, right? But then sorry, the peak time, but then the settling time, as you can see on this simulated one, okay, instead of theoretical, this theoretical, remember, is based on second order system. It's not for this so-called fourth order system, right? Because we have already add poles and zeros over there, okay? You can see that now the systems, it responds faster, okay? But then the settling time, you can see it's almost the same. It settles to the 2%, is almost similar to the previous one, okay? Meaning to say in this case you have to redo, okay? Redo, how we redo? Select a different zero, right? Redo it, okay? So if you redo, then you should able to repositions the whole zero and pose on your lead compensator, okay? So the difference between the lead compensators that you may change is either the locations, okay, the positions of the zero, and then the steady state error and the amount of gain, okay, as well as the approximations of the second order, right? So that is very important, okay? So you may get an invalid approximation in this case, okay? So if we happen to select the zero compensator equals to -4, let's say, right, which would able to cancel out the pools of your existing system, now you would see that the performance, the compensator performance actually improve as what we would want, okay? And in this case the approximation is okay, is valid. All right, so you can see that it have improved, okay? This is the idea behind it. All right, so you can see that when we use different compensator, if we use different PD, we can able to improve the transient response. If we use PI, the integrator, we can improve the steady state error. Now if we would want both happens together, if we want the transient response as well as the steady state error improve together, then we would want to combine them together, right? So you should able to do it, right? First, improve the transient response first, then we improve the steady state response. Okay, this is the idea. Okay, do PD first, transient response first, then improve the system response. Okay, part by part. All right. Alternatively, again, you can use PID, right? So this is where the PID comes into picture. PID with these transfer functions or the lag lead, okay, lag lead compensators. All right, again, lag lead compensators is very similar. Okay, just have to add them both together, right? So in order to implement this PID controller transfer functions, you have the K1, K2, and K3, okay, which this represent the KP, sometimes they call it KP, right, in the PID parameters, okay, because this is corresponding to the P controller, this corresponding to the integrator controller, and this corresponding to the differentiator controller. So you have PID, right? So the KP, KD, and KI, right? So called. Okay, so this is how you can implement it. We may not go into the PID design, okay, because I believe once you understand fully about the PD and PI, then PID is just a combination of it. Okay, solve for the PD first, then solve for the PI. Okay, just follow this step, you would come to the PID controller, right? So the step, just a brief design procedure for the PID. First, you need to find the pull positions to meet the transient response. Okay, remember, we design for the transient response first. Once we get the PD controller, then check whether it is validate or not. Okay, once it valid, then only we design for the PI, okay, which reduce or improve the steady state error performance. Okay, once you come with the PI, then you would able to combine them into your equations to get the K1, K2, and K3. Once you get this, again resimulate to check whether they are valid or not. If not valid, just repeat. Alright, so this is the design. You always do an iterations. Okay, try with one part with certain trial value or starting value of 0 or pulls. Okay, simulate, check again, check again, check again. Right, and that would be your assignment, right? So remember, you have an assignment. Okay, I already posted in the Google Classroom, which you are required to design a PID controller. Okay, that would be your tutorial plus your assignment, right? So make sure you learn it carefully for the PI and the PD part, and then you just follow the step, okay, to simulate and come up with your assignment. Okay, so for the lead lag or the lag lead compensator is similar, right? So you just have these two parts comes together, you just multiply them together, right? The design step also similar. You need to know the desirable pull locations according to your transient specifications, then design your lead compensator, simulate, then if you want to improve the steady state performance, then change or adjust accordingly and design for your lag compensator and simulate again, right? So eventually when we come to the final pictures, okay, this would be the idea. So you can see that the P is encompass the D and the I, right? So you can see that previously I draw with two leg, right, like the D and the P. So in the Venn diagram you see a very odd Venn diagram, but actually because of this PD, okay, the D always require the P to adjust, okay, so that it lies along the root locus, similar to the PI. Okay, when you add a integrator, you need to adjust the P so that it again lies along the root locus. Okay, so therefore it should looks like this. Okay, so you have the PD, PI, or PID, right? So depends on what purpose you want. Okay, now you can have a system, and you can also design a controller to control the system according to your desirable uh, design specifications, the transient response as well as the steady state error. Okay, so that would completes the whole design part on the compensator using a cascade compensator, right? So again, as I've mentioned previously, we will not go in depth about the feedback type of compensator, okay? But then we just have a look on it, okay? The idea behind it, okay? So in the feedback type of compensator or controller, so you would put the compensator at the feedback loop, okay? So you can see that we can break them into again k what k2 or whatever it is, but then we have to break the system into two again, right? Where you may have this so-called minor loop, okay, to deal with the transient response, and you have another loop, okay, to deal with the steady state error itself. Alright, so you may have a combination of minor loop and a major loop. Okay, it may be a bit more complicated because of the looping, which is a non-zero, yeah, a non-zero feedback. Okay, therefore the equations may become slightly complex. Okay, but then if you pay more attentions on your calculations, then it would be fine for you. Okay, but we will not go in depth. Okay, make sure you practice, make perfect your cascade part, then this would be quite handy later on, right? So they are more complicated than the cascade. Okay, generally provide faster response, less noise. Okay, if that is the problem with your previous cascade uh, design, right? So if too much noise, then you may need this feedback type of compensator, and it may not require much of additional gain. Okay, previously you have to adjust a lot of the k value, the gain value, right? But then if we use a feedback type, then that gain value may not be adjusted that much, right? That concludes our chapters for today. So come to the Q&A. If you have any questions, we can have a quick check on this. Let's check. So remember, I already post the assignments in the Google Classroom, and if you notice, I have put 4 to 5% instead of 4 previously. Okay, because I recheck back the previous assignment one. I put 4 to 5, so it will be easier for you to regroup using the same person again, right? So since everything is clear, then we will see you again tomorrow during the tutorial, right? So stay safe everyone, and goodbye for today. Bye bye.